Now that we've been introduced to the substitution rule, the next big question is to identify when the substitution rule is appropriate. And there are going to be, generally speaking, two big things to look for, one of which we've already mentioned. One of them is a composition of functions. And again, we're going to put a little asterisk next to this because there are, of course, some exceptions to the rule. Generally speaking, we're going to make a substitution on the inside function, and in order to have an inside function, we need to be able to identify a composition of functions. However, the other substitution that I mentioned, the differential substitution, is just as important. So with that in mind, the presence of the derivative of the inside function is going to be important as well. Now that's for when we make our differential substitution. To put this in as general form as possible, a substitution is going to be taken anytime we see both of those things. This would be considered a composition of two functions, and this is the presence of the derivative of the inside function. The substitution that we would make is on the inside function. Let u be equal to g of x. For the differential substitution, this is where we differentiate each side with respect to the appropriate variable. The derivative of u will express as du, and the derivative of g of x will express this as g prime of x times dx. What that allows us to do is make a substitution on the first part. F of g of x can now be expressed as f of u. Then the g prime of x times dx, all of that can become du. Now it is necessary to make sure that u is the only variable that is contained within the integral. If there are any leftover x's or t's or thetas or whatever your independent variable happen to be, this technique will not work. So some examples of being able to identify situations where something like this would be appropriate. Let's talk about the sine of x times e raised to the cosine of x dx. The composition of functions that we have in this case would be e raised to the cosine of x power. The inside of those two functions would be the cosine of x. So if I were to propose a substitution for this one, it would be u equals the cosine of x. However, when I do my differential substitution, du would be equal to the derivative of the cosine of x. That is the negative sine of x dx. Now I have a sine of x and a dx, but I don't have a negative. With that in mind, I can alter the form of this substitution so that it is more in line with what's present within the problem. So I can turn my sine of x times dx into negative du. Because negative is essentially saying negative 1 times du, a constant multiple is not going to make or break anything. Reordering this appropriately, I'm going to put my sine of x next to my dx so that we can make the substitution as seamless as possible. So e raised to the cosine of x is going to become e raised to the u power, and the sine of x times dx will become negative du. Because a negative is a constant multiple, it's not going to have an impact, and we can factor it out of the integral. From here, we would proceed to find the most general antiderivative of e to the u du as possible. That would be e to the u plus a constant. At which point, I would substitute back, and I would be left with negative e raised to the cosine of x power plus a constant. The great thing about the u substitution, or the substitution rule, is you can always check your final answer by taking a derivative. And by taking a derivative, you should need to use the chain rule in order to get back to whatever you started with. Now let's talk about the exception to the rule where you're not always necessarily looking for a composition of functions. Now technically there are some tricky ways that you can create compositions of functions without even meaning to. I would like to consider the following. Here is the integral of the natural log of x divided by x dx. Now, on the surface, it doesn't particularly look like a composition of functions. However, I'm going to make an algebraic alteration to this to put it more in a form where you might be able to identify what's going on. Rather than saying divided by x, what I'm going to say is multiplied by 1 over x. You'll notice that 1 over x is the derivative of the natural log of x. Now, back on our last page, we said one of the big things that we need to look for is the presence of the derivative of the so-called inside function. The natural log of x isn't really serving as an inside function, but we can still make a substitution on it and say let u be equal to the natural log of x. For our differential substitution, that means that du is going to be equal to 1 over x times dx. That would be the derivative of the natural log. Now with that in mind, we have a 1 over x times dx contained within the problem. So with that in mind, I can make a substitution on the 1 over x times dx, call that du, and the natural log of x will simply become u. The integral is now asking for the antiderivative of u with respect to u. This is now a power rule problem. This will be 1/2 times u squared plus a generic constant. Then when we substitute back to get this in terms of x, this will be half of the natural log of x quantity squared plus c. And once again, you can verify your result by differentiating 1/2 times the natural log of x quantity squared plus c, and seeing that you will arrive back at the natural log of x divided by x.